I've been really fortunate for a long period of time because I get to see enormous volumes of data from so many different deposits. And one of the observations I would make is that exploration is not rocket science. We make it way harder than it needs to be. And we make really poor use, in general, of pathfinder chemistry. So if you look at the history of discoveries over the last 50 years, we were really good at finding things that stick out of the ground, and we are really house at finding things that are hidden. And the best tool we have to map the outflow zones from blind deposits is pathfinder chemistry. I think the reason why we don't use it very well is because there are so few case studies in the public domain. Right? Think about all the papers you've read in the last 10 years. How many papers have you seen that show the footprints of mineral deposits using modern low detection limit 4-acid digest ICP-MS? And I can think of about 5. Right? So geochemistry is really easy. It's all about pattern recognition. And if you don't know what pattern you're looking for, then you're not going to see it. So when Doug asked me to give a talk here, I thought the best thing I can do, talking about geochemistry, is just to show the footprints of a few mineral deposits. So we get some stuff in the public domain. We've seen lots of cartoons. This is my cartoon of porphyry copper systems. We've seen a few cartoon pathfinder things presented yesterday. None of them showed actual data. They were just cartoons, and none of them showed the threshold levels for the anomalous metals. Right? So that's the stuff you need to look at. So I'm going to show you one example of a porphyry copper system. I'm going to show you one example of a low sulfidation epithermal and one of a VMS. And thanks to the companies that allow me to put this stuff on the screen, and thanks to the people who have helped me collect this data. Good on you, Ned. So a couple of introductory things. What kind of data do you need to collect? On this little table, these are some of the kind of legacy analytical methods we would have used in years gone by. And look at the detection limits for those elements versus average crustal abundance levels, right? I really like these oxyanion pathfinder things, and I'll show you why in the next slide. If you have not used ICP-MS to analyse your samples, you will not be able to map the footprints of those elements. So when you're thinking about what kind of legacy data is fit for purpose, if it's not ICP-MS, throw it out. And here's another thing to think about. This is a little copper gold system I've been working on in the Yilgarn. And I've got 3 cross-sections here. I'm showing sulphur, copper and bismuth on these cross-sections. So there's a little layer of transported material in here, and then there's regolith in here. We can see top of fresh rock that's marked by the dissolution of pyrite and the weathering profile. Right, so all of this stuff here with no sulphur is all regolith. Look at what happens to the copper. Right, in that oxidised material, there is no copper. It's all been leached out. The supergene enrichment down in here. Here's bismuth. Right? So all those things that form oxyanion complexes, like tungsten, moly, tin, bismuth, tellurium, arsenic, antimony, those things hang around in leached regolith. But copper, lead, zinc, gold, silver, manganese do not. Right? So think about what elements you want to use for your reconnaissance work. I'm going to show a porphyry copper system first. Think about the 2 big porphyries in New South Wales. Think about Cadia and North Parkes. The North Parkes complex was discovered by GeoPico in the late 70s. Cadia was discovered in the 80s. That was way before we had ICP-MS. So the biggest and best of the porphyry systems were drilled out before we had ICP-MS as a commercial technique. So the quality of the data, or the nature of the data we have from the drill out phases then, is not very good. So we don't we don't actually know what the outflow of the top of Cadia East or Ridgeway looks like. And we've got a bit of an idea from North Parkes, because John Hoy is going crazy with ICP-MS now, so we're getting part of that picture. And I'll show you a bit of that in a sec. So because we didn't have a really good New South Wales example, I've picked out some other one and I've made it quite anonymous. And rather than showing the point data, I've done these as gridded images. So here you can see the outline of a porphyry intrusion, and this is an image of the copper distribution. And in this case, the ore body is hosted in the porphyry, not in the wall rock. You can see the blue stuff here is less than 100 ppm. Look at what we get at surface. Right? And this is, I shouldn't say what it is. There's no regolith profile developed over the top of this, so we're not seeing depletion due to weathering. This is just a lack of copper at surface. I'm going to go through a series of slides here that go essentially going down a temperature gradient. Right? What we're really looking at is trace elements that are sitting in the lattice of pyrite. And rather than analysing individual pyrite grains, we're looking at a metre of core, so you just homogenise all that signal. So there's a really, really distinct, like every porphyry system looks like this. Every porphyry system. There's variations with overprints, but they all have the same pattern. And what we're really looking at here is a proxy for temperature that we can measure in the pyrite contents, or pyrite trace elements. So that's copper. Here's sulphur. Right, so this is a pyrite shell that's sitting above the copper grade shell, like the Porphyry 101. This is the big pyrite halo. So I'll put that in for reference so you can see where all those chalcophile things are going to go. Here's moly. So there's a little bit less moly in the guts of the porphyry, but you can see the moly now extending out beyond the edges of the porphyry. And if you're seeing a coherent footprint of +5 to 10 ppm moly, that's going to be the trace moly load that's sitting in the pyrite crystal lattice. Right, so big footprint of +5, that's a happy number. Here's selenium. Selenium goes into the high temperature pyrite, so this is mapping proximal phyllic alteration. Here's tin. You wouldn't think of tin being in a porphyry system, but there's trace levels of tin, especially in the white micas, and it goes into the high temperature white micas. And look at this, like that's a screaming, compared to the low background, that's a screaming tin anomaly at surface. If you did not use 4-acid digest, you would not be able to measure this. Here's bismuth, and 1 ppm, that's a big number. Look at the scale, like that's a big bismuth footprint over the top of this thing. You would not miss that. Tellurium looks the same. Here's arsenic. Right, so this is in the outer halo of that pyrite footprint. Right, and antimony will look the same. Here's manganese. So whenever we have really intense phyllic alteration, all the hornblende, all the biotite, all the chlorite gets blown away, manganese goes into solution, and there's always a really sharp front like this. This boundary in here is where we switch from sericite pyrite to chlorite sericite pyrite. So porphyries will always have a big zone of zinc and manganese depletion, top dead centre in the phyllic alteration, and then they'll have a donut of zinc and manganese enrichment in the most proximal propilytic alteration. So here's a little synthesis. John Hoy has drilled out, he's got a bunch of new diamond holes out on this side of Endeavour 26, and he's got a few over in here. So we had about a quarter of the system covered, and I used my colouring in pencils and predicted what the rest of it would look like. And just for fun, I put a 250 by 250 metre grid over that. So imagine if you had been the GeoPico guys in the late 70s and you had a RAB rig and you could analyse stuff with ICP-MS. If you drilled that, if you'd driven out across the wheat paddocks and drilled a grid of RAB at 250 by 250 metres, this is what you would have seen in the chemistry. Right. I'm being really conservative here. You could have drilled the whole of the North Parks complex at 400 by 400, just tagged the bedrock, and you would have found every porphyry in that camp, or you would have found the outflow from those porphyries. You know, every porphyry looks the same, like seriously. And all we're doing here is just mapping a temperature gradient through the phyllic alteration, right? And we're just looking for the hot spots in it. So that's the cartoon. That's in the abstracts. I'll keep going. Don't want to run out of time. The next one is a low sulfidation epithermal system. So I'll give you a bit of context. This is some data that was published last year from the Taupo geothermal system. So this is from Isabel Chamberfort and John Dillis. And they have analysed a bunch of rocks at surface and a bunch of things in the geothermal wells. Right, so we know what the temperature is for a lot of, because these are active systems. Right? Measure the temperature down the bore. We know how much antimony, we know how much cesium is in the rock. And this is plotting antimony and cesium as a function of elevation. So you can see the temperature control and the distribution of these elements. This is super clear. So that's the context, right? So you don't see big footprints of plus 2 ppm antimony until you're below 200 degrees, really. And same with cesium. These are going into low temperature minerals. This is going to be a story about picking the outflow from low sulfidation epithermal veins. So here's a little long section of Pajingo that most people will have seen. Pajingo was discovered because the Scott lode up in here was a big fat banded epithermal vein sticking out of the ground. And once that was found, they started tracking this along strike, and they found Nancy and Vera and so on. The whole host sequence at Pajingo is tilted. It dips from the northwest to the southeast, and all of the main ore shoots occur at about the same level relative to the paleo surface. So now, because it's tilted, as you go further and further along strike, what we're seeing at surface is further and further into the hanging wall, like lower and lower temperature environments related to that system. So if we take all of the gold assays from the drill holes and make a gridded image, it looks like this. So here's the traces of the veins projected onto that map. Can you see that okay? Yeah. All right. Ned Howard started doing this originally when evolution got hold of Pajingo. So Ned started doing some surface geochem just to get an idea of what the patterns around these vein systems look like. And then Chris Chambers and Genesio Siracrosta went nuts, and they just collected thousands of samples. So this is a stunning data set. This is one of the best epithermal data sets I've seen. The gold chemistry in the soils doesn't really map it that well. Kind of surprising. Here's Molly. Right, so up on Mount Janet, there's a screaming big Molly anomaly, and that's kind of like, well, that's any good porphyry, you'd be happy to have a Molly anomaly like that. That's pretty good. And look at the scale. These are 2.5 kilometre squares. Here's bismuth. Right, so bigger footprint. Here's arsenic. So remember, these are the outcropping epithermal veins in here, and these things down in here, the economic vein sections, are probably 500 metres below surface. So here we're seeing the start of a big outflow zone above these deeper veins. Here's antimony, right? This stuff is going nuts. Really dense sampling in here, kind of sparse sampling out here, but the amplitude is the same. So this antimony anomaly goes for 10 kilometres. It's got a really sharp edge in here. Wow, what's that? And this edge is transported cover. So when you get out over to here, on the other side of that little transported basin, there's still anomalous antimony. Like, this thing is enormous. The footprint of Pajingo is at least 10 by 10 kilometres. Here's cesium, so here's all the low temperature clay minerals. So here's my cartoon of what the pathfinder patterns for epithermal systems look like. Imagine if you had some remote sensing data and you mapped out these alteration systems on the ground in the Drummond Basin. You could go and do soil geochem 500 by 500 and you would know what level in that fossil geothermal system you were looking at. It's a great way to do reconnaissance. Okay, now I'm going down to Ross Larger's territory. This is Hellier. Hellier is discovered by Aberfoyle Kew River was discovered in the late 70s. Tony Crawford was a vacation student. He did the first soil sampling program over the top of Kew River. And this was later data that's collected using ICPMS. This is done by Bass Metals. I'm going to start with a map of copper distribution. So here's Kew River, here's Hellier. This green unit in here is the dacite package. So the massive sulfide lenses occur at the top of this dacite, in the contact between the dacites and the hanging wall basalts. Right, so this is the ex-halite horizon. I could actually demonstrate here that in these green rocks, where we see the outcropping alteration, copper is depleted. Right, so you're looking for copper. You're looking for a copper system, and copper is depleted in the footwall rocks, and lead, zinc, manganese are smashed in that footwall alteration, like just completely stripped. The only reason why Kew River was found was because it outcrops, and Tony and his mates took soil samples directly on top of the outcropping massive sulfides. If that had been outcropping, they would not have discovered it with a soil geochem. Here's the arsenic map. That's a screaming arsenic map, and that arsenic perfectly follows the distribution of the sericite pyrite alteration that we see in the footwall rocks. Here's antimony, that's even better. And here's thallium. Right? So VMS systems, that's a hot black smoker system, fluids 250, 300 degrees. It quenches with cold seawater. It makes a really disordered pyrite structure that just sucks up all that stuff. Think about Peter Christo yesterday talking about the copper anomalies in the Mount Chalmers district. He's got copper, lead, zinc, whatever in the soil geochem. I'd be doing something different there. Think about all the porphyry copper presentations we saw yesterday, like the Narromine complex at Mile, inflection. If I had that ground, I know what I'd be doing first. So there's a little cartoon of VMS systems. So I'm going to have a rant now. This is one of my favourite geochem diagrams. This was data that was collected by the Geological Survey of Western Australia 25 years ago. They used to have a program where they would go out and collect surface materials on 250,000 scale map sheets. They would collect 1,000 samples per 250,000 scale map sheet. So that's one sample every 16 square kilometres. And the bottom edge of this map is 100 kilometres north of Kalgoorlie. So this is a map of arsenic. 50,000 square kilometres, there's 3,000 samples in here. You can see the footprint of every orogenic gold system in those greenstone belts with that sample pattern. I won't say this very often, but this is one instance where I'm really envious of geophysicists. that's kind of embarrassing, but we've got these absolutely amazing geophysical maps of Australia. We've got, magnetics and radiometrics and passive seismic and blah, blah, blah. Just amazing. Where's the geochemistry version of that? This is the equivalent of having 1960s BMR mile-spaced airmag data, right? But we can still see these systems. Imagine if we did that with geochemistry. Well, actually we can, because all the data's been collected. It's all open file data, or some of it's still closed file, and it's held by the state surveys. Imagine if we put all of that stuff into a map, what kind of images could we generate from that? Well, this is what you could do. This is a little compilation I've put together from things I've worked on in the past. That's 100 kilometres. I won't tell you where it is or what it is, but there's about 500,000 assays in that image, right? What we're looking for, we are not looking for point anomalies in these data sets. And we are not looking for anomalies in one element. We are looking for clusters of anomalous stuff in multiple elements, and we are looking for the zoning patterns within those elements, because that'll tell you what kind of system it is. It'll tell you something about the lateral zoning, and it'll tell you about where you are vertically within the system. How much would it cost to have database people at the surveys start with the most recent gear and go back in time and put it into one big database like that? Compared to the cost of a geophysical survey, that's pretty trivial. So I'm getting the ding. Hydrothermal systems have really, really predictable and consistent patterns to them. All the porphyries look the same, all the low sulfidation things look the same, and the amplitude of the anomalies don't vary that much. They do have really distinct lateral and vertical zoning, so you can tell where you are in the outflow pathways from those systems. We could sample these at 500 by 500 metres and know, like you would find everything in Australia pretty much, except for some of the Cobar things. You could even sample them at kilometre by kilometre and you'd have a really good idea where to go. You do need ICP MS, and the next discovery, the next 10 discoveries are already sitting in public domain data. Right? Just need someone to put it together. Where's Phil Blevin?